Welcome to the second part of our lecture on proof by induction. So in this second part, we will do some example proofs by induction to practice them a little bit based on the skeleton we introduced last time. And also we will look into sums as sequences, their closed forms, and again, how to prove the correctness of closed forms using induction. So this is just a quick reminder of the skeleton for inductive proofs that we'll use in all of the examples in this part 2. So the goal of induction is to prove a statement of the form P of n is true for all positive integers n. And the first step is to formulate the problem statement, meaning to formulate this P of n. Know that P of n is a predicate and it's formulated variable n, so that when any positive integer is substituted for n in P on n, the statement C is always either true or false. Then in step 2, we have to show that base case holds, meaning we have to prove that P of 1 is true. In step 3, we assume our inductive hypothesis, meaning we assume that P of n holds for some n. And then in our inductive step, which is where most of the action happens, we have to prove that P of n plus 1 is true by leveraging the inductive hypothesis and the problem statement. Okay, so let's see how we are going to apply this skeleton on a couple of simple proofs by induction. So let's do our first proof by induction. So here is the problem statement we want to prove. Let a of 1 is equal to 11 and a of k is equal to a of k minus 1 plus 4 and p of k is equal to 4 times k plus 7. Using induction, we want to show that a of k is equal to p of k for all k. So how do we do this? Well, we are going to follow the skeleton that we introduced in the previous slide. So first, we have to define our problem statement, which is our predicate. So that's our predicate P of n, which is in this case equivalent to A of n is equal to P of n for all n in positive integers. Okay, so that's our first step. The second step is to show that the base case holds. So in this case, we want to show that A of 1 is equal to P of 1, which is equivalent to predicate P of 1, which is our base case. Okay, so how do we show this? Well, we simply compute what A of 1 is. A of 1 is equal to 11. So that's our recursive formula. And P of 1 is equal to 4 times 1 plus 7, which is also 11. Meaning that A of 1 is equal to P of 1. And we show that our base case holds. Okay, now we write down our inductive hypothesis. Let me just underline the main steps. So what is our inductive hypothesis? We assume that A of n is equal to P of n. And finally, we do our inductive step. Where we want to show that A of n plus 1 is equal to P of n plus 1. And we are going to show this using the inductive hypothesis and the problem statement. Okay, so we know from our problem statement that A of n plus 1 is equal to A of n plus 4. So this is the recursive definition from our problem statement. And that is equal to, now we plug in our inductive hypothesis. So we assume that A of n is equal to P of n. And so instead of A of n, we're going to plug in 4 times n plus 7, and then plus 4. So we used the inductive hypothesis here, and we substituted A of n with P of n, which is equal to, if we look at the definition, 4 times n plus 7. So now that is equal to 4 times n plus 1 plus 7, which is equal to P of n plus 1. Great. So what we got is that in our inductive step, A of n plus 1 is equal to P of n plus 1. And that concludes our inductive proof. So by doing this, we proved that A of n is equal to P of n for all positive n. Okay, let us now do another induction example. So this time, using induction, we want to show that for all positive integers n, m is equal to n squared plus n is even. Note that in the previous lectures, we proved this using cases. And this time around, we are going to do it using induction. How do we get started? Well, we are going to follow the 4 steps of our skeleton proof that we introduced previously. Okay, so let's go through the 4 steps. So first, we have to define our predicate P of n, our problem statement. So in this case, P of n is equivalent to, for all n element of positive integers, m is equal to n squared plus n is even. Okay, so that's our predicate Pn. So that's our problem statement. Now we want to prove the base case. So we want to show that P of 1 holds, and P of 1 is equivalent to m is equal to 1 squared plus 1, which is equal to 2 is even. So 2 isn't that even, and therefore our base case holds. Now we introduce our inductive hypothesis. Which in this case will be we will assume that P of n minus 1 is true. And if we write this out, it means that m, which is equal to n minus 1 squared plus n minus 1. So that's what m is equal when we're using n minus 1, which is equal to n squared minus 2n plus 1 plus n minus 1, which is equal to n squared minus n is even. Okay, so that's our inductive hypothesis. And now we have to do inductive step. Okay, so we assumed in our inductive hypothesis that P of n minus 1 is true. And now in the inductive step, we want to prove that P of n is true. So between the hypothesis and the step, you always have to move just by one. So you can move from n minus 1 to n, or you can move from n to n plus 1. Those are going to be the most common examples. You could even do something like moving from n plus 3 to n plus 4, but that usually introduces unnecessary complexity. So typically we want to move either from n minus 1 in hypothesis to n in deductive step, or from n in hypothesis to n plus 1 in deductive step. Okay, so we want to show that P of n is true. So from the deductive hypothesis, we know that n squared minus n is equal to 2k, where k is some integer. How do we know this? Well, because we know that n squared minus n is even from the inductive hypothesis. So now if we rearrange this a little bit, we get that n squared is equal to 2k plus n. Know that from here we want to show that P of n is true, meaning that n squared plus n is even. So we want to work our way to somehow get n squared plus n on the left hand side. So how do we do this? Now we add n to both sides. So we get n squared plus n is equal to 2k plus 2n. Great. So we have n squared plus n on the left hand side. So let's factor out 2. So we get n squared plus n is equal to 2 times k plus n. Okay. Now, because we know that k and n are both integers and that integers are closed under addition, we can substitute k plus n by another integer. So we get n squared plus n is equal to 2 times some integer l. And we can do this because of closure of addition. And this L is element of Z. Great. So now we have that n squared plus n is 2 times L, which means that n squared plus n is even. So here in our inductive step, we prove that Pn is true by using the hypothesis and definition of P. And by proof of induction, we show that m is equal to n squared plus n is even for all n. And this concludes our proof. So one thing that I wanted to mention here is that, as you can see, you can often use different strategies to prove the same thing. And which strategy is the best? It's often hard to say in advance. That's where, in fact, a lot of hardness about doing proofs comes into play. You have to try a couple of different strategies and see which one works the best. In this course, we will always give you a hint about which strategy you have to use in exam and so on. But of course, when you are doing real world proofs, nobody provides you with a strategy. You have to come up with the strategy on your own, which is where lots of the hardness is in doing proofs. Okay, so next we are going to look into how we can express sums as a recursive sequence. So suppose we are given a sequence b1, b2, bk, and so on, and we are told to consider the following summation sequences, where s1 is equal to b1, s2 is the sum from I is equal to 1 to 2 of b i's, and sk is the sum of I is equal from 1 to 4 of b i's. So can this summation sequence S1, S2 to Sk be written as a recursive sequence? Sk is equal to Sk minus 1 plus Bk. Well, if we take a look at it, I think it's clear that we can actually do that. And now the question is also, how is Sk plus 1 is equal to Sk plus Bk plus 1 related to this sequence? Well, as you can see, it includes and refers to Sk. And so we can leverage Sk and plug it into Sk plus 1 while doing our proofs. Okay. So let's show how we would use induction to prove what the closed expression is for a given sum. So here's our problem statement. Given that k of m is equal to this expression, m times m plus 1 divided by 2, and our sum s of m, which is equal to sum of I, where I is equal to 1 to m, which expands into this sum, we want to prove that S of m is equal to k of m for all integers m. Okay, so how do we do this using induction? Well, we are going to follow the 4 steps of our skeleton proof. So first, we have to formulate P of m. And so in this case, P of m is equal to S of m is equal to k of m. So this is our problem statement. And that is true for all m element of z plus. Okay, so that's our problem statement. Now we have to show base case. So we want to show that P of 1 holds. So P of 1 is equivalent to S of 1 is equal to K of 1. Okay, so what is S of 1? S of 1 is equal to 1. that follows from the definition of S, and k of 1 is equal to 1 times 1 plus 1 divided by 2, that is also 1. So we showed that S of 1 is equal to k of 1, and therefore we showed our base case. Great. So step 3, we have to assume inductive hypothesis. So what is our inductive hypothesis in this case? We are going to assume that P of n minus 1 holds, meaning that S of n minus 1 is equal to P of n minus 1. Great. And now, as usual, the key part of our proof is inductive step. So in inductive step, because we assume that P of n minus 1 holds, in the hypothesis, we want to show that P of n holds. Meaning that S of n is equal to k of n. And I just noticed I made a little mistake here. So this should be k of n. So our hypothesis is that S of n minus 1 is equal to k on f of n minus 1. Okay, so how do we prove our inductive step? Well, let's write down the recursive expression for the sum. So we have S of n is equal to 1 plus 2 plus 3 plus n minus 1 plus n. And that is equal to, well, if we look at the first n minus 1 members, that's exactly what S of n minus 1 is. So that's equal to S of n minus 1 plus n. Great, so we expressed S of n recursively as S of n minus 1 plus n. Now we can deploy our inductive hypothesis and replace this S of n minus 1 with k of n minus 1. So we get S of n is equal to k of n minus 1, that follows from the hypothesis, plus n. That is equal to n minus 1 times n divided by 2. So that's from the definition of k plus n. So that is now equal to n squared minus n divided by 2 plus n. So that is equal to, if we do a little bit of algebra, n squared plus n divided by 2, and that is equal to n times n plus 1 divided by 2, and that is equal to k of n. So we show that S of n is equal to k of n, and hence we proved the original problem. And this concludes our inductive proof of this problem. So let's try to prove another closed form for sum using induction. So this time we want to show that if S of n is equal to this sum here, and B of n is equal to 1 minus 1 over 3 to the power of n, then S of n is equal to B of n for all n. Okay, coming back to our 4 steps of induction. First, we want to define our problem statement. So we have to define our predicate P of n. And in this case, it is equivalent to S of n is equal to B of n. Wonderful. Now we want to show base case. So we want to show that P of 1 holds, which is equivalent to S of 1 is equal to B of 1. So what is S of 1? S of 1 is equal to sum I is equal from 1 to 1 of 2 to 3 to the power of I, and then it's equal to 2/3, and B of 1 is equal to 1 minus 1 over 3 to the power of 1. That's also equal to 2/3. Okay, so we show that S of 1 is equal to B of 1, and we proved our base case. Now we have our induction hypothesis. So we are going to assume P of n minus 1, which is equivalent to S of n minus 1 is equal to B of n minus 1. Great. And now we have to do our inductive step. We want to show that P of n holds, meaning that S of n is equal to B of n. So how are we going to do this? The same as in the previous proof. First, we are going to write out S of n recursively. So S of n in this case is equal to S of n minus 1 plus 2 over 3 to the power of n. So this follows from the definition of S of n. And now, the same as before, we want to leverage the induction hypothesis, and we want to substitute this S of n minus 1 with B of n minus 1. So we get that this is equal to B of n minus 1 plus 2 divided by 3 to the power of n. And now we plug in the definition of B of n minus 1, and we get that this is equal to 1 minus 1 um, over 3 to the power of n minus 1 plus this leftover guy 2 over 3 to the power of n. Okay, and so that is equal to, we somehow want to add these guys together, so we get 1 minus 3 to the power of n, and here we have 3 plus 2. And that is equal to I messed this up a little bit. My algebra is wrong. So let me clear this up. So let's try to do this maybe in an easier way. So that's 1 minus 3 over 3 to the power of n plus 2 over 3 to the power of n. And that is equal to 1 minus 1 over 3 to the power of n, which is exactly what Bn is. So we show that S of n is equal to B of n in our inductive step, and that concludes our proof. So by doing this, we show that S of n is equal to B of n for all positive n. Okay, so we'll conclude with this example problem. And in the next lecture, we'll do a bit more of induction, and we'll also introduce some new proof techniques that we haven't seen before. Thank you all for watching, and I'll see you on Tuesday.